Well, when we're talking about exponential growth, and in particular when we're talking about things like maybe like, for instance, population, well, we've looked at population of bacteria and things like that, population of state of Georgia and other things. There's generally a cap on that. In other words, if you look at an exponential graph, let's say we got a graph here and we got an exponential function, it's going to be characterized something like this, where it just keeps rising very rapidly out towards infinity. But when we're talking about populations, well, there's usually a limitation to that. I mean, if we're talking about population of people, for example, I mean, is there enough food? Is there enough places for people to live? Are there enough jobs in that area for people to be employed? You can have diseases and other things. Is there enough water to sustain the population? And so generally there's a cap on that, and we can express that by what we call a logistic growth model. And the graph of a logistic growth model is going to look something like this. In other words, there is a limit to where the growth is going to stop. And it actually forms a horizontal asymptote. Now, the basic logistic growth function goes like this. If we got f of t time equals c over 1 plus a times the natural base e raised to the power of b or k, in our book it says b for this logistic growth, times, that's negative b, times t. Okay, and this c here, it represents c, the reason why it's given that value, it is a constraint. And in other words, it's saying, in the case of population, we're not going to exceed that amount. And that forms both a horizontal asymptote and it would define what the maximum population is. So let's take a look at this problem that we got here. Population of a certain species of fish in a lake after t years, a certain number of years, can be modeled by the function p of t, function p of t, equals 1880 over 1 plus 1.42, the natural base e, raised to the power of negative 0.037 t. Now this 1880, in answer to these first two questions, what's the horizontal asymptote? So that the graph of this function is going to look something like that with whatever the values are along the x and the y axis. Well, the horizontal asymptote is going to be at 1880. It's not going to exceed that level, and which is also the answer to the second question. What's the maximum population of fish in the lake? Well, it's determined that it's going to be 1,880. Now we're going to jump over to the next slide, and we're going to be asked the question when, so we're going to be solving for t or time, will the population reach a certain amount using this formula right here that we have been given in this example. All right, let's move to the next slide. So we're being asked then here, when will the population reach 1,875? So it's getting close to that limit of 1880, but not quite there. So if we're going to solve this, then we're going to say that when P of t equals 1875 equals, and then our logistic growth model was 1880 over 1 plus 1.42e raised to the power of negative 0.037 t. Okay, well, let's multiply both sides of this equation by the denominator so we can clear it out. Then we'd have 1 plus, let me put that in parentheses, 1.42e raised to the power of negative 0.037t, close my parentheses, equals, no, plus, times 1875 equals 1880. Now we're trying to solve for t, so let's divide both sides by 1875. That would leave us with 1.11 plus 1.42 natural base raised to the power of negative 0.037t equals 1880 over 1875. Well, we got 1 plus, so let's subtract 1 from both sides. This would give us 1.42e raised to the power of negative 0.0037t equals 1880 over 1875 minus 1. Well, now if I'm going to subtract 1 from this, I've got to express it in a fractional form, of which I can do that. So I could rewrite this then as 1.42e raised to the power of negative 0.037t equals 1880 over 1875 minus 1875 over 1875. That is, in fact, 1. And then that's going to leave me with 1.42e raised to the negative 0.037t equals 5 over 1875. We'll move our calculation up here. All right, I'm going to use the product property, and I'm going to take the log of both sides, the natural log of both sides. So when I do, I'm going to then have ln 1.42 plus ln e, again, of negative 0.037t equals ln 5 over 1875. Well, my ln and my e's are going to cancel right here. So then I've got ln 1.42 plus negative 0.037t equals ln 5 over 1875. Now let's subtract the ln 1.42 to both sides, which then would leave me with negative 0.037t equals ln 5 over 1875 minus ln 1.42. Then I can divide both sides by the negative 0.37 to isolate the t, and then I've got t equals ln 5 over 1875 minus ln 1.42 divided by negative 0.037. And when I complete this mathematical computation right here in my calculator, then I'm going to end up with t, the time it's going to take for the number of fish to reach 1,875. T is going to be approximately 170 years based on this logistic growth model. It's fun, isn't it? Well, at least we get to apply our skills There's people that actually do stuff like this, if you can believe it. Maybe it'd be one of you.